Hey everyone, it's Stephen Allegri. I'm here to just give a kind of brief tutorial, or look into the visualizer I made for visualizing SemNet results. It can visualize both single target nodes with its respective source nodes of a certain kind, or comparisons between different target nodes, which is actually that was like the kernel or idea that actually led me to work on this in the first place. So hopefully it can do that, right? But yeah, I'll go ahead and just get started. Delete that. Okay, so you want to use the visualizer. First, you have to kind of refigure your data and make it compatible with the scripts I wrote. So this is okay. All right. So this right here. This is what you might clone from GitHub or download from somewhere. This is what I'll probably upload. So it's a folder that contains a couple different things, 2 different test data folders. This lib folder, which contains the libraries for my JavaScript, HTML, CSS trio. This is said trio, a README, and a Python script, which takes the SemNet data and turns it into JSON, which is a important intermediary between the SemNet data and the visualizer. So first things first, the data. Let's look at this. So it's broken down where you have a main data, directory, right? Click in here. You have a subdata directory, where I guess this is the main data directory with subdata folders. You enter that folder and you enter a new directory that has the kind of source node you're dealing with, right? And to go even further, that folder that has the kind of source node, kind, type, whatever of source node, that is where the data is held. And so why is it organized this way? Okay. So when you run a SemNet simulation, let's say, at least if you're running a SemNet simulation to be visualized by my visualizer, right? If that's the intended goal. Say you want to run a simulation that compares, say, hypothyroidism and Alzheimer's disease. Find all the source nodes that connect those 2 different target nodes of type disease or syndrome, or amino acid or peptide protein. But let's just say disease or syndrome in this case. So you find all those source nodes, but they have to be ranked in respect to some target node, right? That's how the head of some score is made. Now, because there are 2 targets, there have to be 2 different sets of rankings. And each of those rankings are kind of seen here in the 2 different data files, right? And to kind of break down the structure of the data file naming scheme itself, which is also kind of a finicky thing when it comes to the visualizer. The naming scheme has to follow this naming scheme exactly, which I'll explain in a little bit. But either way, so this is data that actually compares sleep to impaired cognition, finding all the sources that link those 2 of type disease or syndrome. And you can see that it's broken up by underscore. That's actually how my Python script kind of takes data out of the naming scheme of the file. So each underscore breaks up the file name, and then it might take this information here, the source, the disease or syndrome information, the target source, the name source, or the target name information, all that stuff. That's going to be used by the Python script. But anyway, this is the naming scheme. You can see and read more about it in the README. It goes into a little bit more detail there. And if anything, you can just shoot me an email or watch the this is the video, but I don't know, just watch what I do with all this stuff. But either way, so this is the data. Okay, so it's comparing these 2 different things. We want to visualize it, so I'll go and open it up. Okay. So this is what SemNet spits out. And you're like, okay, so I have these source nodes for both these data sets, which these source nodes should be the same, just ranked differently. Let's see. So this is 218, technically 217 source nodes. Same thing here. 218, technically 217. Okay, so all the source nodes are the same, but they're ranked differently because they're ranked in respect to different target nodes. So in this case, this is ranked in respect to impaired cognition, impaired cognition. Speaking of which, and then this one isn't ranked in respect to sleep. So you can see that the top ranked source node of, that share between these two targets, in respect to impaired cognition, is Alzheimer's disease. Okay, that makes sense. When it's in respect to sleep, it's sleep disturbances. Fair enough. Okay, but we want to compare these. So what my script does is it looks at these two SemNet outputs and it says, okay, all these had some scores that goes from 4.9 to 16.7, and this one goes to, or from 6.5 to, 17.65. Those ranges are different. First, you have to normalize those so that they can eventually be compared. So what happens is this 16 turns into a 1, this 4.9 turns into a 1, and then these are all normalized based on that scale, or into a 0, a 0. And then these are all normalized based on that scale from 0 to 1, 0 being the most impactful or most associated, 1 being the least. Same thing here. This will be normalized to 0. This will be normalized to 1. So these will all be on the same scale. And now we have to take the average of these normalized Hedison scores. Because you can see that when we're investigating the relationship of these source nodes with respect to both target nodes, we want a source node that's highly related to both of them, not just one of them or the other, but both. So in this case, let's take, on this sheet, sleep disturbances, ranked number 1 in respect to sleep. Now, whereas in respect to impaired cognition, 25. So this is ranked 1 here. The best source node in respect to sleep of all the source nodes. This one, in respect to impaired cognition, is ranked 25. Somewhat middle of the pack, still high, but not super high. So by averaging these, you kind of see how impactful that source node is in respect to both. Because this ranks it very highly, this ranks it less highly. Taking the average finds a little middle ground between those two, and you can say, okay, sleep disturbances are somewhat related to both things. Okay, now let's take Parkinson's. It's ranked 2 in respect to impaired cognition, and then it's ranked 3 in respect to sleep. So it's highly ranked between, in both of these situations. When normalized, it'll be Parkinson's disease will be very close to 0, on both of these, within both of these data sheets, and therefore when they're averaged, Parkinson's disease will most likely be towards the top. And we can actually kind of take a look at that once the simulation starts running. Okay, that's the data. That's kind of the background of what's going on. Let's do some running. Okay, so this is what you'll get from GitHub, an email, who knows, this folder with all this information. I made this local visualizer folder that has, actually I'll delete that because I've tried this once. Okay, this is my visualizer folder, completely empty. I will copy this into this, like you might do, who knows. Okay. So SemNet Visualizer version 1.0 is now in my visualizer folder. I open this, cool. Okay, so first things first, I have to run this Python script, SemNet data to JSON, because I need that JSON information to actually run my JavaScript. So I use PyCharm, so let me open that up. This should be quite straightforward. Open. Let's go to that visualizer. Let's open this directory. Bingo. Okay, run that directory. Let's deconstruct that. Let's use this interpreter. Okay, cool. Oh, come on. Okay, cool. All right, let's open up that Python script. So these are the 4 packages I use. Quite straightforward. It's all in, the Conda environment, which I'm actually using right now. And this is what the script is. It's 515 lines of sheer pain, at least on my end. So, and I guess maybe just to push this point home, this is actually the function that reads in all the information from the file names. you can see it's broken up by these underscores. That's what the string is split into. So it's delineated into these different broken up, I guess, indices of that string list, and that's where all this information comes from. So you might get like the name, the source node name, the target name, ID information, all this kind of stuff from the actual title of the file itself. Maybe a shortcut, but that's where we're at right now. So it is what it is. Okay, let's go down here. Let's try to change this to data, because that's the flashier of all the two data sets. Oh, shoot. Okay, there we go. Run. And there should be no problems here. This can take anywhere between 5 to 20 seconds. It depends on how big your data set is. This is a pretty big data set. It's comparing like 4 or 5 different target nodes, so it's quite robust. But usually it's less than 5 seconds. So, okay, it's done running. Let's check that folder. What? What is this? Nodes links output. Is that what is that? A JSON file? Oh my goodness. All right, it worked. Okay, so step 2. Run the JavaScript. And that's why we made the JSON file in the first place, right? So before we actually run the JavaScript or JavaScript, HTML, CSS trio, we have to actually start a Python server, because some libraries that are used in the JavaScript script require libraries that load data asynchronously, which is you need a server for that. It's kind of complicated. I still don't even 100% understand it, but I know when it comes to web development stuff, you have to have a server going for this kind of visualization. So let's do that. But thankfully, it's really easy. So let's open up a command prompt inside this directory. So you see that I opened it in this directory, but you can move to that directory within the command prompt itself if you so choose. And let's type out Python http.server 8000. So that starts up the server. Cool. And let's open that. That's my calendar. It's not super interesting. All right, localhost 8000. Let's see what's running in there. Oh, look, it's all of our stuff. I've obviously used this server before, so it's kind of purpled out, but either way, this is it. Okay, so we have the data, we have the server. Now we just have to click, where is it? The HTML file right here, JSON to 3D graph. And this is where it gets fun. Let me bring this up. Boom. Awesome. Okay, so what is this? Well, you can see 1, 2, 3, 4 target nodes. So we have impaired cognition. I cannot say that word today. Sleep, Alzheimer's disease, and hypothyroidism. Those are the target nodes. And these are all the source nodes that link all 4 of these target nodes, right? So these are the source nodes that link impaired cognition and sleep. These are the source nodes that link impaired sleep, Alzheimer's disease, and hypothyroidism. And these are the ones that just link hypothyroidism and Alzheimer's disease. And let's see if we can find their mirrors in the data sheet. Okay, so data 1, disease or syndrome. This is the triplet. Okay, so this is the comparison of using the target nodes, hypothyroidism, Alzheimer's disease, and sleep. Hypothyroidism, Alzheimer's disease, sleep. This is the data right here that creates these source nodes right here. Because, and again, what my Python program does is it compares these two, compares this and this then. It compares these, right? It has every single one of these data sheets compared to the other at least once. So was that 3 or... 7, 2, yeah, 3 factorial or something like that, just to get the comparisons down, or maybe 3 factorial over 2, whatever the math is, I forget. But all that combinatoric stuff is used here to get all these different comparisons, and these are seen here. Okay, let's see data 2. Whoa, 7 different kinds. Those are represented by all these that link. Well, what do they link? Alzheimer's disease and hypothyroidism. Alzheimer's disease, hypothyroidism. And all these different colors represent different kinds of source nodes. So these light green are disease or syndrome. So sleep apnea obstructive, disease or syndrome. Parkinson's disease, disease or syndrome. What's the purple? Antioxidants. Probably an organic chemical. Yellow looks like amino acid, peptide, or protein. Teal is memory impairment, so mental or behavioral dysfunction maybe. I don't know. But either way, so that's where all this data is coming from. And then, yeah, you can finally see data 3 is the comparison between sleep and impaired cognition. Wow. Which are these source nodes right here. Cool. Okay, so let's see what kind of fun things we can do with this simulation. So, okay, this is somewhat informative. But, you know, say we want to see what the most relevant source nodes are in respect to all these different target nodes. This bar helps kind of filter this out. So the normalized hedison is the average. Let me actually click this button. So before I get ahead of myself, this button helps you stick, like allows you to stick nodes, right? Boom, stuck. Unclick it, click, unstuck. Cool. But let's stick some nodes. Okay, so the normalized hedison is the average of these 3 red lines. And what I mean by that is atherosclerosis, ATH. I'm bad at pronouncing things, so I'll just call it ATH. ATH in respect to sleep has some normalized hedison score, let's say 0.26. ATH in respect to hypothyroidism has a normalized hedison score of 0.11. ATH in respect to Alzheimer's disease has a normalized hedison score of 0.16. These all averaged up give you the normalized hedison score of ATH, okay? And this helps you filter that, okay? So this normalized hedison score is the average of all these different links and is therefore the quote-unquote normalized hedison score for each source node. So let's look at this. Let's see all this data. Whoa, okay. Let me unhook that guy and stick nodes. So when it comes to a lot of data, it'll take a little bit of time to for the graph to load because again, it's rendering in the browser, so it'll eventually become smooth, but it might take a little bit of time. Yeah. So you see here, it's like nice and smooth, right? Okay. So this is all the data, and you can see that these are like different, are a little bit more opaque, less opaque. Bigger, smaller. The smaller and more opaque the source node, the less relevant it is, which it's probably obvious, right? And these different connections, these red lines that connect these source nodes to, let me stick these nodes. Yeah, okay. I don't know what he was doing over here. But these red lines, it's kind of hard to see, but this one's a little bit redder. This one's a little bit pinker. These are shaded and, you know, on a scale of like white to red. There's like some HSL stuff that goes into that. But the short of it is, the more red this link is, the more relevant it is. Okay, so let's unstick that. Okay, move around. There you go. Now, this is going to be a little bit computationally intensive, so I'm going to break this down to only a couple. Look at that. And this is easier to read, too. So let's find the most important nodes. So apparently let's connect these. Bingo. Okay. So of the source nodes that connect sleep, AD, and hypothyroidism, obesity and metabolic syndrome are the most important. Let's try and verify that. One, two, three. Okay, so it said obesity and metabolic syndrome. Metabolic syndrome is ranked quite highly here. Metabolic syndrome, decently high here. You know, rank 9. It's okay. Rank 8 here. And rank 2 here. So all those averages come together to have it actually ranked in the top 2 as far as average head-of-sims, normalized head-of-sims go. What's the other one? Obesity. Obesity is ranked 7 here. 10 here. And then 4 here. Okay, so those, whatever those normalized head-of-sim scores are, averaged, get obesity in the top 2. That makes sense. You would be able to perhaps gain that from just looking at the data sheets, but that's the truth. I'm going to close these, actually. So don't corrupt any files. Okay. So let's, finish this off with some button explanations. Stick nodes. That should make sense. When this is red, the nodes stick. Cool. Now you can click it once and it unsticks, no matter what. But yeah, you see these are stuck now. But if you unstick it, now these will just shoot back. Stick it, they stick. Unstick it, no more. So let's unstick that. Okay, cool. So these should all be unstuck. And center camera. Say you're all the way. What? Look at that little fellow. What? Where's my simulator? There it is. It centers the camera. Awesome. Oh my goodness! I'm observing this extremely interesting hypothyroidism node. Oh, but we're back. So that's what center camera does. Gets everything back into perspective. So yeah, that is the simulation. That's the visualization. Hopefully the data... let me preface this by saying the hardest part is getting the data folders correctly oriented and the naming scheme correctly oriented. Now, let's see. The README should have plenty of information on this, but if not, email me at sallegri3@godtech.edu. So there's that. And for the sake of my renderer, I'm not going to go into the script itself, but there are 2 functions. I think generate CSV. If anyone's willing to work on these, please do and send me an update, because what generate CSV does is it generates a comma separated CSV value, I guess, file with all the information that's like the normalized head-of-sim score, the average head-of-sim score, all these different things they're output on that CSV, but it doesn't work for triplets or singles. So that could use some update, because I made this entire simulation to compare 2 different target nodes, and so that's a artifact of that era. That's also to be updated. Also, I think top average head-of-sim is another function, if I remember correctly, that it takes. It essentially does what this bar does, but for different pairs. So if you called top average head-of-sim on the sleep and impaired cognition pandas data frames, which are formed in the Python script, if you said the top 5% of source nodes, it'd probably shoot out Parkinson's disease and Alzheimer's disease. Top 10%, it might do the next 4, 5, 6, 7 top source nodes. That's what that function does, is it finds and it names the top average normalized head-of-sim scored source nodes. But that one, again, works with doubles. So if anyone wants to work on that, please feel free. But yeah, also, I guess one last thing before I go. I'm going to do this for another data set so I can kind of show you what that looks like. Cool. Now, sometimes this doesn't work, but let's see. Bingo. So new data. Awesome. Look at these cute little nodes. So this is a single. So this is, if you only ran a SemNet simulation for hypothyroidism, and you said, I want all the source nodes for hypothyroidism of type, it looks like amino acid, peptide, or protein. And I'll only want that in respect to the target node, it can do that. So if you only did that, ignore this, you would see just this, right? And then it still works with the sliders and everything. This is just to show that these can be separate. So yeah, that's that. And one last thing, if for some reason you run the Python script and you update the data, but it doesn't update in the browser, what I do is I go to, nope, don't inspect the page. let's go to settings, go to clear browser data, and then clear the cached images and files. That'll just clean your browser of all the data, the cached data, and it should load quite easily from there. So, okay. That's going to wrap it up for me. So I hope that made sense. Any questions, just email me. Yeah, thanks.